Good afternoon. My name is Yubo from Huawei. Here I want to present our work optimizing the file system on heterogeneous memory by integrating DRAM cache with a virtual memory management. Okay, in the traditional storage architecture, the bandwidth and the latency gap between the DRAM and the block device layer is very large, and at the same time they have the different storage semantics. So as we know, the DRAM cache is an important component of the file system. However, when the PM comes, it brings a new storage architecture for the FS desires, which include volatile and non-volatile memory layers. The research found that simply adopt the legacy file system to the heterogeneous memory is insufficient because the software overhead will be very significant. So they try to remove the DRAM cache from the file system, heterogeneous memory file system. However, when the real PM is available, we found it is not perfect enough due to the limited latency, bandwidth, and the concurrency, of course, compared to the DRAM. So this work try to answer the question, do we still need the DRAM cache in the file system, the heterogeneous memory file system? And if yes, how to build an efficient cache framework for it? Okay, now let's use a simple experiment to show the shortcomings of the existing cache and DAX framework. We perform random read and write 10 GB data with 2 MB I/O in single thread. And our first observation is that there's no winner between the cache and the DAX because the performance gap between the PM and the DRAM cannot be ignored. So the data locality is still important for the performance optimization in the heterogeneous memory. At the same time, we think DAX is an overkill in many real-world scenarios because most application is designed based on the POSIX interface. Then our second observation is the data transfer. The data transfer overhead between the file system and the application buffer is significant. From the experiment, it can take up more than 20% of the total overhead in cache-based file system, and more than 90% overhead in the DAX-based file system. And the third observation from this experiment is the cache text, and it's very heavy, which mainly include the overhead of the data synchronization and the data migration. For the data synchronization, such like the background dirty flashing, it can lead to more than 30% of performance declines, while the data migration, such like the cache mishandling, can lead to more than 60% performance decline. Okay, let's take a look of a typical workflow in the cache system. In the read operation, if the cache miss, if the cache hit, we can simply copy the data from the cache to the application buffer. But when the cache miss, we have to look up the PM index and then load the missed page to the DRAM cache and then execute the data copy. In the write operation, the workflow could be a little bit complex. We need to build the cache index if the cache miss, and at the same time, if the background flashing is running, it will block the front-end write I/O. So the motivation of our work is to integrate the DRAM cache with the virtual memory management. And our first design principle is to automate the data transfer between the application and the DRAM cache by the zero copy manner. At the same time, we try to reduce the two-level index overhead. And the second design principle is to reduce the impact of the cache tags. However, the cache tag is difficult to fully remove from a cache system, but we can hide the data synchronization and the data migration overhead on the background. Next, I will introduce the overview and the API of FLAC. In fact, FLAC is a programming framework for the file system developers, and we mainly focus on the data management. The first API is the init FLAC, and it will create a FLAC space, and it is a kernel memory space which can transparent the DRAM cache and the PM for the upper level user, and it will return the address of the FLAC space to the file system developers. Then FLAC provide two data transfer API for the developer to transfer the data between the FLAC space and application buffer by the zero copy manner. And these two API is similar to the copy from user and copy to user API in the kernel. Next, FLAC provide the pflash API for the developer to synchronize the data in the DRAM cache to PM automatically. Finally, FLAC allows the developer to reclaim a range of FLAC space by calling the p3 API. And there are two key technology in the FLAC. The first one is the zero copy caching, which is designed for optimizing the application cache, optimizing the data transfer between the application and the cache. And it will create a heterogeneous page table in the kernel, and it will explore a unified and continuous virtual memory address space for the developer, which can dynamically map to the DRAM or PM as the page is cached or evaded. At the same time, we replicate the PTEs of the FLAC space on the PM for the recovery. Then FLAC proposed a new memory mapping interface called page attaching. So by using the page attaching, we can execute the FLAC-based read and write by mapping the physical page from the source address to the destination address. So by this way, we can avoid the expensive data copy between the application and the cache. For ensuring the security, page attaching will set the page to read only after the page mapping. So the next update on this page will trigger the copy on write page flow. Okay, then the second key technology of FLAC is the parallel automated cache management, which is designed for reducing the impact of cache tags. And we propose a two-phase flashing mechanism for data synchronization. And take an example in the figures. If we want to synchronize the P0 and P1 from DRAM to PM, then the first phase is the collection phase. It will create a temporary buffer and map this buffer to this two page. And at the same time, we have to lock the target PTEs of the FLAC space to avoid the write I/O to change the PTEs mapping during the collection phase. But fortunately, due to the page mapping is fast, so the lock time will be very short. And in the second phase, the persistency phase, it will copy the data from the DRAM cache to the PM. And this phase is expensive, but it is lock-free. So it means that the front-end write I/O can be executed in parallel when the data persisting during the data persisting. And after the flashing success, we will reclaim the temporary buffer and the old version page in the DRAM. Next, we design an async cache mishandling mechanism to automate the data migration. For example, if application 1 in the figure try to read the page 2 and page 3 to its read buffer, but at this time the page 2 is not in the DRAM cache. But we can simply directly attach both these two pages to the read buffer, and this is thanks to the memory semantics of the PM hardware. And then FLAC will asynchronously load the missed page to the DRAM cache in the background. So by this way, we can hide the expensive loading overhead in the data migration on the background. Okay, let's put everything together, and I give a simple example to show how FLAC works. So let's assume that we have a physical page in the PM, and it mapped by the FLAC space. Now, when the application reads this page from the FLAC, the first step is to map the application buffer to this physical page. And FLAC will asynchronously load this page to the DRAM on the background, and then change the PTE mapping. And if the application updates this page, the copy and write page flow will be triggered for the security and isolation. So the page will be copied to the new location, and the application buffer will be remapped to the new version of page to absorb the next updates operation. Then application write back. If the application write back this new page to the FLAC space, we only need to map the FLAC space to the new version of the page, and then reclaim the old version page in the DRAM cache. And finally, if the background flashing is running, the FLAC will synchronize the page to the PM by the two-phase flashing mechanism, and then reclaim the old version page in the PM. Okay, all those FLAC promising some good performance, but it still miss some challenge. The first challenge is to handle the page unaligned I/O. So we design a sliding window buffer to solve this challenge. FLAC asks the application to use the SW buffer. It's a short for the sliding window buffer to proceed the buffer management, and SW buffer will map all the pages containing the recorded data to the buffer, and then use a sliding window to denote the valid data in the buffer. And the second challenge is to reduce the copy and write page flows overhead. For this challenge, we designed two automation API, the bfold or the batch fold, short for the batch fold, and the detach. And FLAC asks the application to call bfold or detach before they reuse the rewrite buffer. For the bfold, it's mainly designed for the case of the application need to process the data in the buffer. And it will batch the data copy and the TLB flash to reduce the copy and write page flow overhead. And for the detach, it's mainly designed for the case of application just need reuse the space of the buffer. So in this case, we can simply map the buffer to some empty page in the batch. So the next update on the buffer will not trigger the copy and write page flow anymore. Okay, then we implement a user space library file system called FlacFS to show how to use FLAC. And FlacFS includes two areas. The first area is the metadata area, and it's built on the normal shared memory, which created by the mmap or shared memory get APIs. And the data area of FlacFS is built on the FLAC space. The metadata is organized as the KV pair and stored in the inode hash table. And we keep the hash table, this hash table, both on the DRAM and the PM for the performance and the recovery. And the file data is stored on the consecutive address. And we borrow this design from the CTFS. And by this way, we can leverage the MMU to accelerate the page indexing. And for the consistency, we design a FS and FLAC collaboration logging mechanism to ensure the whole system consistency. The key point of this mechanism is to put the FS level and the FLAC level metadata into the same log entry, and at the same time, the FLAC used a log structure manner to flash data. So By this way, the FlacFS can ensure both the metadata and the data consistency. Okay, now I show some experimental results, and we compare the FlacFS to the SOTA DAX-based file system like Nova, Speedup, CDFS, and also compare it to the typical cache-based file system, the ext4, which is designed based on the VFS page cache. Okay, in the read-write operation, the FlacFS can outperform other file systems by more than one order of magnitude in this operation. And the main is mainly benefit from the zero copy design and the high concurrency data management. And we also found that FLAC have a better scalability than other file systems, especially in the DAX-based FS suffer from the low scalability due to the concurrency limitation of the PM. We also evaluate all file system on the fsync operation. And all those fsync is not friendly for FlacFS. Is still comparable to the best DAX-FS, and is better than the ext4 in this workload. The main reason is that the FLAC is very lightweight, so it does not introduce a very expensive HR overhead even we bring the DRAM cache back to the heterogeneous memory file system. Then we evaluate the impact of the I/O size on the FlacFS, and we select the I/O size range from the 4 kilobyte to 60 megabyte, and from the result we can find that the FlacFS is more friendly to the I/O size larger than 64 kilobyte. The key reason is that the data copy is not the biggest bottleneck in the small I/O. So FlacFS is more friendly for the larger I/O. In addition, the I/O size larger than the 64 kilobytes common in the production. For example, in the database logging or machine learning checkpointing are the typical large I/O scenario. And next we change the cache evacuation threshold to evaluate the impact of the DRAM cache size. And when the threshold is set to 60 gigabyte, there is no data evacuation in FlacFS. And the result so that the performance does not decline significantly as the threshold decrease. And this is because the page evacuation is efficient in FLAC. Next, we evaluate the impact of the page alignment, and FLAC used the SW buffer to handle the unaligned I/O, and the results show that the unalignment has a little impact on the I/O larger than the 64 kilobyte. And because the main overhead of the SW buff is to copy the data from the original page to the unaligned part, but the copy size will not larger than a page, just 4 kilobyte. Therefore, the impact of the SW buff decrease as the I/O size increase. And next, we also evaluate the impact of a copy on write page fault. We rewrite the buffer in different proportions or by memory set after each file access. And the result so that our automation, the B4 and detach, can reduce the copy on write page fault overhead by more than 70%. Next, we select 3 common applications to show FLAC in performance in the real world. Among them, the grip is the read intensive workload, and tar is the read-write intensive workload, while big sort is a merge sorting application. It is a read, write, and compute intensive workload. it was known that all automation like bfold and detach are used where they are appropriate. And the results show that FlacFS has up to 6 times performance improvement compared to the DRAM file system, and 9 times performance improvement compared to the DAX cache-based file system. At the same time, the bfold and detach is efficient in the real-world scenarios. Okay, conclusion. This paper analyzed the cache and DAX solution on the heterogeneous memory, and we designed a FLAC cache framework and built a prototype file system called FLAC on file system, FlacFS based on it. And the results show that FlacFS has orders of magnitude performance improvement in the micro benchmark and several times performance improvement in the real world application. Okay, thank you.